We continue with decimal for fractions. Today we're going to prove a fact that a fraction m over n would be pure recurrent decimal if and only if the n, the denominator, is relative prime to 10. The GCD n 10 is equal to 1. That is, n would not contain prime factor 2 or 5. Now notice that all the periodic decimal can be expressed in some fraction of some number over a bunch of 9s, right? So we need to show if n is relative prime to 10, we want to show that n would be a factor for some number that's a bunch of 9s, or 10 to the k minus 1, right? So we need to prove that for one direction, and if and only if we need to prove both directions. Let's start from here, right? So if we know n is relative prime, so what we rely on is what is called the Euler theorem. That is extension of Fermat-Little theorem, which is very famous, right? That's for the prime number modulus. But here, Euler theorem is regarding the general modulus n. What we're saying that if a and n is relative prime, then a raised to the what is called phi, which is Euler's torsion function, that counts how many numbers that are relative prime to n. Okay, for prime number p, the phi p would be p minus 1. All the numbers smaller than that is all relative prime to p, right? So that's a fact we're going to rely on. In this case, we're going to use the a to be number 10 because 10 and n is relative prime. So when we apply directly the Euler theorem, we're going to get this. Yeah, so 10 raised to some power is congruent to 1 mod n. What that means is that for some integer m prime, we're going to have m times m prime is going to be equal 10 raised to the 5th power minus 1, right? So that's what we know. Now notice that n would be a factor of this, right? So here this would if that is the case, we can expand the denominator to that power. You can multiply the original fraction by m prime, right? So we get this. Now here, notice that in this case, this would be pure recurring decimals. Okay, we have proven that. Okay. All right, so that's the proof. And the other direction, if we have a fraction, we know for sure that is pure recurring decimal. We want to show that n is relative prime to 10. Okay, so how to do that? So here, notice that since the analysis from the previous video, we know that this pure recurrent decimal would be equivalent to some fraction where the denominator is all 9s, it's a bunch of 9s, right? And there's some integer m prime. M prime is the integer whose digits are just d1, d2, and dk. Yeah. All right, this we know from earlier lecture. So this just rewrite this fraction here, cross product equal to each other, right? Now we notice that n and m is relative prime. Yeah. So the GCD of m and n is a kind of reduced fraction here. So we know for sure that n is going to be divisible by this denominator here. It's a bunch of 9s. Now since the number is a bunch of 9s, so n cannot contain 2 or 10, 2 or 5, right? Because 2 is not divisible with numbers that's considered all digit 9s. 5, neither does 5, right? So that means n should not contain any 2 or 5 prime factor. That is, GCD was equal to 1. Okay, so we have proven this in both directions. Now we're going to look at the case where the n does have prime factor 2 or 5. And that is, it actually not relative prime. We want to show that it would produce a mixed recurring decimal. Okay, recall that in the previous lecture we already showed if you have a mixed recurring decimal, how to convert that to a fraction, right? So we have some examples. You can go back and check out the video. But today we want to prove that if the denominator n has some factor 2 or 5, then it will be a mixed recurring decimal, right? So we're going to start with the example here. The denominator contains some power 2 and 5. Note that s and t could be 0 but cannot be both 0, right? M prime is another number that is relative prime to 10. Okay, so how to deal with that? Okay, for this example here, the denominator here contains 2 and 5, and also something 13 that is not 2 and 5, right? So we claim that this is going to be a mixed recurring decimal. In order to show that, the steps to do first is to convert 2 and 5 to power of 10. Okay, so we choose the higher power, which is 3. So we're going to turn this whole thing to 10 to the third power by multiplying 5 squared, right, on both numerator and denominator to make the denominator power of 10. Okay, and of course for the m prime we're going to keep it as is, right? So for 2 and 5 we want to turn that into 10th power. Okay, so in general what you do is, if you do that, now you can split this fraction into the product of two fractions, right? Now the first part is just when you have 10 to the third power in the denominator is equivalent to move the decimal point to the left by 3 positions, right? So, but the second part we already showed earlier that if the denominator is relative prime to 10, it will produce a pure recurring decimal. So the second part is pure recurrent decimal. Notice that here we're going to have 5 squared, which is 25, is bigger than the denominator. In earlier example, we always assume n is smaller. Now the numerator is smaller. When numerator is bigger, you're going to have integer part of it, right? So in this case, we consider that. All right, so in general, what do we have is, okay, for the fraction here, we turn the n to be 10k times m prime, right? Now, that means in the numerator, you have to multiply, k minus s or k minus t, where k, what is k? K is the bigger value of s and t, right? So one of these would be 0, right? So in the early example, the k is 3 and s is 3, so you don't multiply 2, you multiply 5 power, right? So here, this whole thing would be a new number m prime, yeah, m prime. This is a new integer here. So you have two parts. This part is just pure moving the decimal, and the second part, we can argue that that's pure recurring decimal, right? So let's do that analysis here. K is the max of s and t. So m prime, notice that this time could be bigger than m prime, just like our previous example, right? So 25 is indeed bigger than 13. So that means this fraction here is pure recurring, but it may contain integer part. Okay, so for example, the second part may contain an integer part w. That would be the integer part, and the remaining part is going to be pure recurrent decimal here, right? Now, once you move the decimal back to k digit, you would get this. Okay, so this is called mixed recurring because there is some non-recurring digit, we call it transient digit, in front of the recurring one. Okay, so we have the proof. That is, the GCD, if it has common factor 2 and 5, then you will have mixed recurrent decimals. Now notice that we're going to try with an example here. 56 is 7 times 8. 8 is 2 to the third power. So we would have this trick here, just try to apply here. So what we get is we're going to multiply 5 to the third. Okay, so this would be some integer greater than 1, and then it's actually 17, the integer part. So it's going to be 17, and the pure kind of recurring decimal here. And then the original value 1/56, you just move the digit to the left by 3 digits, right? So it's become 0.017, and then repeating. Okay, so that's the steps. Okay, so in summary, what we learned earlier is that if n is just 2 and 5 only, then it's going to be finite decimal, is terminating decimal, when n contain only 2 or 5 prime factors, right? Some 2 raised to something power, 5 raised to something power. Otherwise, if it's relative prime, does not contain any 2 or 5, then it's pure recurrent decimal. Now, other case, if it contain both 2 and 5 and some non-2 and 5 prime, then it will be mixed recurrent decimal. Alright, so that's what we learned so far. Okay, what we're going to look at next is, for the pure recurrent decimal, what is the period length? What is the relationship of the length with n? Alright, for example, this number 109 is very long. It has 108 digits here. But some other number, 137, which is a prime number, but then the period length is much shorter than 136, right? So we're going to look at that in the subsequent videos. All right. So in the meantime, you can look at some other problem like this. In the meantime, please like, share, and subscribe to the channel.